actually get the buckyballs of the fullerenes, discovered in 1985. It was of interest then and still. So this is a 1D, zero-dimensional object for physicists at least. And you can also take the sheet and you can roll it up, and you get the carbon nanotubes discovered in the early 90s. And that also caused a lot of interest. And then finally, sort of the circle in terms of dimensions were closed when graphene was discovered, or I guess exfoliated in 2004. So graphene is nothing else than a simple sheet of graphite. And I guess for physicists, though, condensed matter physicists, graphene is by far is the most interesting material now. Though a couple of months ago saw a plot over the number of publications for all these four materials, and it turns out it was as many publications still per year with carbon nanotubes as for graphene. But I guess they might have moved sort of towards material science and chemistry. Let me just put on this slide also explain the free electron picture of graphene. So you have the honeycomb lattice at two sites per unit cell, A and B. The first brilliant zone is also a hexagon. And I'm exclusively going to talk about the upper and lower pi bands, so I'm going to completely ignore all the electrons that contribute to the bonding of this material. So you have very strong sigma bonds that you get from sp2 hybridization, if you remember from high school chemistry. And left is then one pc orbital per carbon atom. These orbitals you can very simply couple with a nearest neighbor hopping. This was done already in 1946. And you get the lower and upper pi band. And at zero doping, the Fermi surface will be exactly in between here. So in fact, you don't have a finite Fermi surface at zero doping. It's just a Fermi point. And it's also known as a Dirac point because the spectrum coming out here is linear. And this is a Dirac particle, and it's massless, you don't have a gap here, but of course the speed of light is being replaced by the terminal velocity is smaller. For graphite, you can just keep this number in mind. The CC bond distance is around 1.42, so that's the distance here in plane, but the interplanar distance is more than 3 angstroms. So to a first approximation, you can think of graphite as essentially almost independent of graphene. Okay, so that was a crash course in graphene. You've probably already seen this, but let me now get into what I want to talk to you about today. I first want to show some evidence, both experimental and also some theory results that show that maybe one should at least think about what electronic correlations do in graphene. They sort of standard pictures that you have is direct fermions. They're very weakly interacting, so we ignore the interaction. But I think there are enough evidence that one should at least think about what interactions do in the system. I'm then going to show you how we approach this problem, how we model these correlations, and show that that can lead in, if you have enough doping, in fact, can actually lead to a D-ray superconducting state. We'll talk a little bit about something known as graphite-sulfur composites, and we'll introduce those shortly. Also going to show that you can enhance the superconductivity in Josephson junctions, and these are junctions that have been manufactured recently, so it's really experimental development. And then I'm going to end with some more recent work on magnetic impurities in graphene. It actually turns out that these magnetisms, which are the same electronic correlations that can give rise to superconducting correlations, also give rise to magnetic enhancements. Okay, so let's start with the first point here. So these are some data from a few years back. This is it's a little bit hard to interpret, but this is a magnetic resistance versus applied field. And when you sweep up the field, you get this solid line, and when you sweep down the field, you get the dashed line. Now, if you didn't have any hysteresis, of course, these curves would fall on top of each other, and you would reach a minimum at 0. If you have a ferromagnetic solution or a homogeneous superconductor, you will reach this minimum on the negative side. That is, the dashed line would have been on top of here. But it turns out they measured the dashed line under the solid line, and they have a minimum at positive field. And at least according to the author, and authors, and as far as I know, the only system that actually we know that experiences is granular superconductors where you have Josephson coupled grains. Turns out that it actually reaches minimal positive field. And here is just the differentials, and it turns out in this particular sample this effect went away around 8 Kelvin, but they had samples where it less than 25 Kelvin. So this is maybe weak evidence, but there seems to be something very interesting that goes on in graphite. So this is in graphite, I should say. The graphite sulfur store is much more solid that its superconductivity there. However, graphite sulfur composites, as a rather complicated material. You essentially take graphite and take sulfur and you grind them together, and you need it. What sort of saves you a little bit is that no one has been able to discover any additional phases or compounds or impurities. It really looks like you have chunks of graphite sitting next to sulfur in these materials, and there aren't that much, there aren't any interfacial phases here. And the superconducting behavior is very typical for type 2. You have the magnetization versus temperature. You heat in zero field, you get this curve, and then you cool in field, and you don't retrace, and TC is where these two curves start to depart from each other. So here TC is around 30 Kelvin. The same group, or actually several groups, had measured TC up to about 60 Kelvin. Most maybe are around 30. They also conclude that superconductivity is located to the graphite planes, but it's a very small volume that's superconducting. This is a very clear sign of superconductivity, but you don't have any zero resistivity, so there's no bulk superconducting state. It really seems to be an interfacial state that's located on the graphite side. And I'm not showing that here, but it turns out the superconductivity ferment is actually coexist in some of these samples.
Why it's always so small?
Well, I would explain it with that it's an interfacial effect between the graphite.
But if you grind it better and better?
Presumably you can get higher.
So far nobody succeeded.
Yeah. So, I mean, there's some variation, and also the samples seem to be somewhat heat and age sensitive, which also precedes the material interfacial changes.
So the 60 Kelvin is just coming from this magnetization curves only, or is there other?
Yeah, no, those are from these sorts of curves.
I mean, you said that zero